Greetings, everyone. Today I would like to talk about a new Rodless lumbar stabilization system that we've developed. These are my disclosures. Most significant is the ones highlighted in yellow, called Duet Spine and Box Spine. These are the companies that I am marketing this device through. Before we developed this device, we analyzed the mechanisms of failure of our current systems. One of them, of course, is rod fracture. And then, of course, there is rod loosening when the set screw comes loose. And finally, pedicle screw fracture. To really get an idea of what was going on, we went to the MAUD database. That is the manufacturer and user facility device experience. And that records theoretically all of the failures of our systems. I'm sure many are missed. Nonetheless, we reviewed 10 years of failures, which included more than 17,000 failures. What we learned was that 45% of the failures occur from breakage, primarily of the screw, 42% from migration and detachment, that's when the set screw comes loose, and 10% from deformation of either the screw or the rod. And that's what these slides point out. Screws tend to break, set screws come loose, and rods tend to migrate, and there's a small percentage where the rod or the screw bends. And these are the components, again, showing exactly that. The majority are either screw or set screw failures. Now, why does that occur? If you look at a profile of our standard universal screw, the set screw and screw itself only contact the rod in three places. Right here where the set screw comes down to the top, and down two here on the bottom on each side. That means that if the set screw comes loose even 1/4 turn, it is no longer attached to the rod itself. The other thing to note is that in our standard pedicle screw systems, in order for the head to be universal, we have to narrow the screw right at the proximal portion, and that's where it tends to break. So if we look at these then, 24% of our failures are due to set screw loosening, 14% of our failures are due to the rod itself, and 45% of our failures are due to fracture of the screw. That accounts for 83% of our failures. Well, if we could construct something that eliminated those 83%, obviously we're going to be in a more beneficial position. And what we've done by doing that was, number one, eliminating the plate by attaching it to the primary or first screw. The second thing we did was modify our set screw so that rather than contacting the rod in three places, it contacts the secondary screw 360 degrees. So we get a very tight thing. Finally, the last thing we did was, because we no longer have a universal head that has to move, we could thicken the proximal portion of the screw and eliminate those fractures. Finally, the last thing we did was make this in the form of a triangle. Triangle is the strongest biomechanical device in the universe that we know of. That's why our houses are made in triangles. The Eiffel Tower is made in triangles. Our bridges, even our airplanes, are made basically from triangles. So we wanted to capture that in creating the new device. This is what it looks like in a sawbone, and the x-rays of that showing a bilateral or adjacent level constructs. Because the screws are only 5.5 millimeters and go in at different angles, we can put them side by side and they fit very well. Now, there's a huge prevalence of need for spinal surgery, from degenerative disc disease, herniated discs, osteoporosis, lumbar stenosis. So what we did after devising this device was, of course, we have to test it. And we use the standard ASTM F1717 mechanisms. So for example, for static compression, all of these various tests are performed to see how strong the device will be. When we compared our device to a standard system predicate, under maximum load, our system Duet displaced less than 1/4 of that of the traditional pedicle screw system. And when we went to static compression bending, to move 1 millimeter required 111 newtons for Duet and only 50 newtons for Genesis. This is one of our earlier constructs called Trivergent, and even that wasn't as strong as this construct is in static compression bending. And if we look at that over here, this shows that at 360 degrees, 360 newtons, we only displaced about 4.2 millimeters. Under much less, at 400, it displaced 18 millimeters for our predicate. So we're at least 4 times stronger. And to give you a visual picture of that, this is pre-test and this is post-test in our system, and the same down here, pre-test of our predicate, post-test of our predicate. And you can see how it bent and how this bent up here compared to that. So physiologic compression stimulates bone growth, and the optimal mechanical stimulation is between 1 and 3,000 microstrains. And that's normal for a healthy person. Below 100, we start resorbing bone, and that's what's happening to our astronauts. Above 3 to 4,000, we get micro damage to the end plate, resorption, and fractures. So the average pressure created by a single interbody cage is 4,000 microstrains. This increases if you flex or if you're fat, and that's what creates our subsidence and pseudoarthrosis. So due to Duet's stiffness, it maximally unloads the end plate microstrains, thus it more closely approximates physiologic microstrain and therefore should minimize subsidence and pseudoarthrosis. If we then look at static torsion, Duet, as you can see, to move 1 degree required 20 Newton meters for Duet and only 5 Newton meters. We're looking at this side over here, 20 Newton meters for Duet and only 5 Newton meters for Genesis. So we're at least 4 times stronger in static torsion. And that's what we can see right here as well, static torsion for 20 Newton meters in Trivergent and Duet. And looking at it visually, pre-test and post-test, can't even tell the difference compared to our standard pedicle screw system, which completely fell apart. Now, if we look at dynamic compression bending or fatigue, 4 out of our 5 tests of Duet went out to 5 million cycles at 250 newtons. Only 1 of our predicate went out to 5 million cycles, and that was only at 150 newtons. So once again, Duet and Trivergent, an earlier system, are significantly stronger than our predicates. So the clinical impact of this is that compared to the predicate device, the Duet system was stronger in all aspects. It demonstrated more stiffness in compression bending, which unloads the abnormal microstrain on the end plates. It displaced only 1/4 as much as the predicate under maximum load, further minimizing abnormal microstrain. It's 2.5 times stronger in torsional strength, which greatly increases its torsional stability, particularly in the context of a facetectomy, such as with TLIF, thus decreasing the possibility of construct failure. Finally, by eliminating the rod, by eliminating the narrowed stem on the classic pedicle screw, and by modifying the locking cap, we can minimize up to 83% of our current failures. This comes sterilely pre-packed, making it very cost-effective and ASC friendly, but that we can discuss perhaps in another talk. Thank you very much. I'm happy to answer any questions.